Okay. Hi, good afternoon. My name is Jose Matute, currently serving as a research associate working with Professor Kermorini. Together with Mr. Tian Fabakun and Mr. Daniel Tobias, we have been working on the development of a testbed of connected and automated driving shuttles for rural environments. So our motivation is pretty aligned with most of you have been, or the previous presenters have been talking about. This is safety. Around half of the fatalities in North Carolina have been happened on rural roads, according to a statistic from 2020. So the idea is to reduce this number using advanced technologies such as automatic driving system. The project goal is to address these challenges associated with the deployment of this kind of vehicles, such as in rural roads, such as lack of road infrastructure, limited connectivity, narrow roads, unpredictable obstacles, and limited mapping data. So the objectives of this presentation is to demonstrate the technological developments that we have been achieving with our testbed, and also to demonstrate some of the results that we have obtained from our test track that tries to be like a rural environment. So some related projects have been supported by NCA&T since 2020, and particularly currently it is being supported by the US DOT under the CR2C2 project. And specifically, we are part, as the previous presenter said, part of the project 2-3, developing connected mixed transit vehicles for equitable mobility service for rural and underserved communities. So the use case one of the use cases that I want to present you today is our rural test track that is located at the Gateway Research Park. I hope most of you can attend to our demonstration tomorrow afternoon there. So some facts about this rural test track. It has some, we have tried to include most of the features that you can find on rural test tracks or in rural roads, like irregular intersections, 2-lane changing to 1-lane, pedestrian crossings, bike lanes, roundabouts. Also, we have a monitoring room that is in our lab, in the space that we have there, where we can track the position of these connected vehicles. Some of the results that have been I'm going to show you are related to the usual autonomy software stack. We have been working strongly with AutoWare Auto, is one of these open source autonomous software stack that are available for research and development. And so we have been working on several parts like mapping, the trajectory planning, object detection, and human machine interface for the vehicles. So this is one of our shuttles. We have all setup that we have been improving together with the projects that we have been participating. So it consists on one Velodyne LiDAR on the top. Also, we use Novatel Power Pack as a secondary localization device. We use cameras on the front, and also a radar on the front rack. We have a previous computer that was substituted by newer ones, and also we have been including more sensors to these platforms, like more cameras pointing to the front and the sides. The same for more LiDARs to cover the blind spots on the sides and also on the front of the car. And as I said, including more computing power, trying to test how it works if we separate the perception from the planning and control side, so each computer can handle each of the tasks. So our software architecture, I will be presenting some results related to mapping, then localization, the planning and trajectory tracking, and the object detection and response. This is more or less the usual flow of this kind of autonomous systems. So specifically with the mapping, so we are using an open source mapping algorithm is LIOSAM. So you need for this a LiDAR device, of course, and also global navigation satellite system, and you can use the odometry and the LiDAR to create a point cloud map. Then with that point cloud map, what we do is to create a semantic map information, and in this semantic map, you can include information about the number of lanes, the maximum speed that you can drive, if you have parking places, if you have crosswalks. And on the side, you can see how the system works with LiDAR localization. It is continuously matching the points from the point cloud map with the current measurements. In the path planning and tracking, so it is separated in several steps. The first of all is the global planning. So here is where you are located and you define where is the point where you want to go. So you are defining from point A to point B trajectory. Then in the local planning, you can check if those maximum speeds that are from the semantic information are there, and if the system is properly tracking those speeds, and if it is keeping on the center of the lane. Also, all these tests are in this rural test track that I presented before. This is the behavioral planning working. So the behavioral planning includes what the vehicle should do if there is a stop sign, for example, or if there is a crosswalk, what is the behavior that the vehicle should follow. In this case, it is stopping 3 seconds in the stop line, and then it continues if there is no object or something in front of the car. And finally, the path tracking. This system, you can select the algorithm that you prefer for path tracking. In this case, it's using pure pursuit algorithm, but we have others available, MPC and some others from our own development. Here, so once you have the plan of the trajectory, and then you track it, then you can have some objects in front of you, like pedestrians. So in those cases, the car is capable, or the system, to detect those objects and then respond accordingly. This case is braking because it's a pedestrian in front blocking the road. But there are some other cases where the pedestrian, but it already crossed the street, so it doesn't mean that there is an object in front of the car, so it's safe to continue. This is an example of how the object tracking system works. So here we are using LiDAR fused with cameras to locate the cars that are parked on the sides. And the same with dynamic objects. So we have been doing tests with static objects, dynamic objects, and yeah, measuring the accuracy and how can we can improve those systems. The other use case that I want to present you is a demonstration that we had last year here in transferring people from our university to downtown Greensboro. So this was a 1-month pilot program. We gave free public rides connecting A&T campus and downtown. It has only 2 stops on these red globes here. It was connecting both places and also the neighborhood in the middle of the ride. It was 2 hours a day from 11 to 1 p.m. It took around 2-minute trip from each place to the other one and then going back. The maximum speed is 25 miles per hour. This was a limitation from the testbeds that we are using. Of course, the top speed on the streets is 35 miles per hour. And some facts that we obtained from, or some results that we obtained from this demonstration. So we were capable to drive 127 miles, around 12.7 hours in autonomous mode. We transfer around 180 passengers, and the most important is that we had no accidents during this demonstration. This is a picture of the three shuttles driving on this section of the route. And of course, this couldn't be possible if we haven't had the sponsors. Some pictures from the system working on this demonstration. So there's autonomous navigation, detecting objects, following the path. We also developed a live shuttle track app, so anyone with a cell phone could track where is the position of the vehicle and then go to the shuttle stop and take the ride. So that wasn't necessary to wait for them. And then this is how the system was working in case of pedestrian crossing in front of the car. Some of the ongoing research that we have is what to do in rural environments that have like a lot of trees around. So initially we have thinking of using just GPS for localization, then rural environments, and in some cases this is not possible. So we have to use another source of localization. In this case, we are using LiDAR. We didn't expect that it worked, but it amazingly works really well, LiDAR localization. So we use the fusion of both sources to improve the localization. The other is what to do in case of challenging terrains. Rural environments has a lot of irregular roads, so this affects other systems like control. So what happens if we have disturbances in positioning, in the geo measurement of the car, on the speed, or in the actuation sensor of the vehicle? So we have been working on developing robust controllers to handle these kind of situations. Some other works that we are working, being redundant, is so trying to solve driving through non-standard intersections. Also understanding rural environments, some objects that are not commonly on urban settings, and then driving under weather and lighting conditions that can differ. And also we are working on the integration of our task of scheduling with others, for example, like routing or pick-off, drop-off of passengers, and the same integrating it with community selection and assessments. These are some publications from the researchers in our group. And we also have some posters from researchers in our group that are available, that you can check them out if you are interested. So thank you.